Hey guys, I'm going to go over binary table in LogixPro. It is right here, B3 binary table. The reason we're talking about this is we started working on student programming exercise number 4 on the door simulation, and this is the first time that they had us use a bit location. It says you can also use integer table. It also says integer table bits, but a bit is a binary digit. It's either a 0 or a 1. An integer is not a bit. So that's kind of a weird way to phrase it, to flag specific conditions. So you're going to use a binary. I'm going to show you a couple of examples of how you would use these binary bits because there was some confusion there. And what they actually are, they're just a location in memory that you can use for anything that you want. Also, right after this, I'm going to make a separate video on OTL and OTU instructions. So if that's what you're looking for, that's going to be in a separate video. But yeah, again, right here is where exercise 4 for the door simulator. All right, up here is our X. This is what switches back and forth between our simulation. If you're working on the door simulator, it will look more like this. And you'll hit this X. It doesn't close your simulation. It just takes you to the folders list that you'll see in the real Allen Bradley software. And if you hit the X there, it just takes you back to the simulation. Nothing actually gets closed. This is just kind of toggles back and forth. There's a bunch of little weird intricacies about this program, and this is one of them. This should be like a toggle. It's not actually closing a window. So your first folder here is going to be your output table, and then you're going to have your inputs. These are going to be the physical outputs and inputs on the PLC. So your PLC, if it's a MicroLogix, across the top will have all your inputs, and across the bottom will have all your outputs. That's going to be something that a wire connects to. We used this status bit. You'll see that everything is zeros here. If I put the processor in run mode and I go here, you'll see this is a free running clock that's counting up in binary. If I change it from binary to decimal, you'll see it's just the number that's going up and up and up and up. When we use it in binary, you'll see like this bit specifically, 5 right here, you'll see it has a frequency that stays the same. So it goes 1 0 1 0 1 0. So we can assign a contact to this memory location. Every time it's 1, that contact will be true. Every time it's 0, that contact will be false. And the same with all these other ones. This is how we did the flash in the project before this. So we covered our outputs. That's going to be the physical outputs on the outside of the device. The inputs, that's going to be the inputs. You're going to have wires connected to them going into the PLC that you're going to wire up your push buttons and sensors and switches to. Your status bits, the only one that you're actually going to use frequently is going to be this S4 row here. And you'll see each one of these is a group of 16, so it's 2 bytes. A byte's going to be 0 through 7, and 8 through 15 is going to be the second byte. That's 8 bits. So 0 through 7 is 8 bits going across here, and 8 through 15 is the second group of 8 bits. So altogether we would call this a word, 2 bits, or 2 bytes, 16-bit word. There's also 32-bit words sometimes. Our next data table that we get down to is our binary table. This is what we're talking about. Our binary table is nothing other than a large group of bits in the memory. So these are all just individual transistors inside the processor that are not being used by the processor or anything else. They're just for your own use to store information. So they can be a 0 or a 1. So I'll give you a quick example of a way that you would do that. So these can be used the same way. They have to be tied to an output to change status. And they can be used the same as you would use if you think of a relay coil, you'd turn the relay coil on, so it would go from off to on, or 0 to a 1, and then there would be associated contacts with that relay that would switch states. So think of this as your coil, and then you can make as many contacts as you want associated with this memory address that are all going to change state when you change the state of this location from 0 to 1 or vice versa. So I'm not sure if that makes it a little easier to follow, but I'll draw some simple examples of what exactly this is. And the address doesn't matter. You can pick any random one. I usually start with the lowest one. So B30 would be the lowest word, 16-bit word right here. And bit 0 right here would be the lowest bit in that word. So if you're going to start with the lowest one, sometimes you have to use a lot of these. So I usually start with the lowest one, and the next one I get 1, and the next one I get 2, and just go through in order to make sure I don't pick the same one over again or whatever. I don't just pick random ones throughout, obviously. It's rare that you're going to use more than 16 of these in a single program, so this top row usually suffices for whatever you would need. So here we go. I'm in run mode, so I can't edit. I'm going to flip that over so I'm not in run mode anymore. Close this. I'm going to make my ladder a little bit bigger. And I'm going to add some extra rungs here. I'm going to add some extra rungs here. There we go. Sometimes it lets you press it multiple times, and other times it does not. It's another intricacy of LogixPro. LogixPro specifically, RSLogix 500 and Allen Bradley has its own quirks that are different than this software are. So we are going to add an regular OTE output. It's going to get dropped in on the left. It's going to pop over here. And we are going to set that to our very first bit in our binary table. And then we are going to put a contact here. And we will use the IO simulation. And we'll take the address from that first switch. Now if we download this and run it, if you right click on anything, you can go to data table and it'll bring the data table up, because sometimes it's hard to navigate to it when the processor's in run mode. So here's the table I'm on right now. I'm on the outputs. That's not what I want. So this little pull down right here, I can select binary. And the very top right one is what this output, this OTE, is going to switch. So if I press this switch, it will make the left side of this rung true, because this is going to close. It's going to go through, it's going to energize my output, my OTE, that's associated with this bit location. So if I close this, that's true. So when it evaluates this rung, it'll say this side's true, the output should be true. So it makes this output true, so it changes that bit location to a 1. Now if I open this back up, that turns off and it changes that bit location back to a 0. And you might say, how is that helpful? What is that going to do for me? This doesn't have to be a switch, this can be a sensor, this could be an overheat temp sensor, it could be a proximity sensor, this could be anything tied to this bit location. And then you could have, normally, this is just one example, there's lots of ways you can use this. You could have a series of normally opens down here for every rung. Sometimes we'll make a stop-start circuit up here, and this will just be the enable. Goes there, and I'm going to need a stop. That's normally open, so that's not going to work. Let me stop. So you can use this OTE associated with that bit location the same way that you would have a normal stop-start. So I'm going to make that my stop. So I will just leave that one closed. I will make it this address, and I'll just leave this switch in a closed position. Then I'm going to associate all of these with that. Download this and run it. Apologize for not labeling anything. So I'm going to leave this closed because in a physical stop button, it has normally closed contacts, so you're always going to have a signal coming in on that. That's why it's normally open, but it's closed right now. And again, Allen Bradley does not use this terminology. They use XIO and XIC, but just for our purposes here, we're going to call them normally open, normally closed. So right here, when I close this is going to simulate the start. And it's going to click that. You're going to energize this OTE and change that bit location to a 1. When that changes to a 1, it's also going to change this to a 1 or true or closed, and it's going to bypass my start button, so I can let my start button go, and it's going to latch in just like a normal relay does for start, or your normal stop-start circuit that you rate with regular outputs over here as opposed to the binary table locations. So I press this and it latched in. Now assuming this is a momentary start push button, it would pop back open, but we would still be latched in and this would stay on. So all of these are on. Now if you want, so these could be anything. There could be different lights on here, different motors, different whatever, and a lot of times this will be called the enable bit. So when you hit start, it enables all the other rungs because it's the first thing in the rung and they're all normally open. So this has to be true for any of the other rungs to operate. So an example of that would be if I put some outputs down here and I make them go to some lights, maybe I'll put an S bit in here too. So right in there, I'll go to my status bit and grab like 5 maybe. And I will put some lights over here on these outputs. Used to doing this on a laptop, so this big monitor, I feel like I gotta look really far from side to side. Now I'm going to download this and run it. So my enable bit is true, which allows all these other rungs to execute, which means this one's going to flash because I have the S4 bit going to the output for this LED. The next one's on solid on rung 2, and then on rung 3 that one's on solid. So if I hit this stop here, everything dies. If I hit the start, well, so this would be a normally closed for a stop, so it would momentarily open and then close back again. And then when I hit the start, everything's enabled again. That's like a simple explanation, but you can have an enable bit and you can have 100 rungs that all have this in the front of it. So if you hit stop there, it just kills everything in the entire program. There's other things that you can do, like, let me go offline here. So you could call this one like the warning light. Cut this, cut that, and this could just be cut there, cutting everything. Sometimes you'll get the screen in this situation, and if you haven't been here before, it's hard to figure out how to get the other tile open again. So it's up here. There's 2 sets of this minimize, restore, and close. It's not the top one, it's the second one down, and it's in the middle. If you click that, then it'll get back to where it needs to be. So in this scenario, I'm going to say this is a temp switch. That's a temperature switch, and when this temperature switch is going to be normally open when whatever device that we're measuring the temperature on crosses the threshold that that temperature switch is set for, it will close this temperature switch. That will enable this bit to go true, which will allow it to close this contact, and it'll start flashing this warning light. So I need to worry about that secondary one right now, and I will open this up so it doesn't start right away. Hit download and hit run. So here's our temp switch. Our tank's heating up and it just crossed over the threshold that this temperature switch is set for, and it's going to close. Now we have a yellow flashing light letting us know that our temperature is too hot, it's overheated. You could have multiple other things. Down here you could have a fan. So this would go to a physical output. So our lowest available output is this guy. This would go to a physical output. Oh, I already have that set as the light. Change that to 1. Edit it. Fan. And you could also have the heater. So if your heater output that was causing the tank to heat up to begin with, drag that down to there and just edit it this way. Call this the heater. And this is going to be a normally closed over here associated with that same bit location. So now what's going to happen is, let me download it. Okay, right now everything is good. The heater is running. That green light right there, right here, the heater is on. Our tank's warming up. It's getting closer and closer. Now and there's no warning lights. The fan is not on. This temperature switch makes, because it gets too high, it changes this 1 bit, which change all the contacts on these other rungs. So on rung 001, it enables the warning light. Now we have a warning light flashing, letting us know that it has overheated. The second rung, for that output, I just have it going to this red light, but really it would be going to a fan. So it overheated. We have a warning light letting us know. We have a fan that kicked on that's blowing it on to cool it down. And also the heater got cut out because it had a normally closed associated with that bit right there that opened up and killed power to the heater. So we turned off our heater, we turned on a fan, and we have a warning light saying that it is overheated currently. And that is all through this. So you could do the same thing like you do with relay logic, and this could just be an output. Like this could just be your lowest possible output location, but that's a physical output on your PLC. There's a screw terminal on your PLC or on your output card that's gonna change state. It's gonna send a signal out through that if you use an actual output in your output folder. These are all actual outputs that are gonna change state on the exterior. It's not an internal bit that you're using. This the reason that you don't want to do that on something like the small micrologics are, some of those only have 6 outputs. So if you use actual outputs to do this kind of relay thing, if you do that like twice, you took a third of your possible actual outlets up, and then you can only have like 4 things that are actually connected to it that are being controlled. But you have a ton of internal bits that function the same as a relay coil, and then you can make unlimited amount of contacts associated with that, and some of them can be normally closed, some of them can be normally open. It doesn't matter. They're all just going to switch state whenever you energize or de-energize that bit location. And you're not really energizing or de-energizing it like you do when you say that. Generally you mean a coil and a relay or a contactor, but what you're really doing is just changing the state of that bit location from a 0 to a 1 or a 1 to a 0. So then it goes to the second rung, and it evaluates the left-hand side. So everything's read from top to bottom, left to right. It'll evaluate rung 001, and it will say bit location 3/3:0/0. It'll look at the bit table and say that's a 1. So that's true. So we got through there. Then it'll look at your S4 bit, and that's flashing. So half the time it'll get through there. But every time it goes through to evaluate, it looks at the left-hand side and says, should I update the output table to make this output true or false? So every time this turns on, it'll update it to true. Going down to rung 002, it'll evaluate the left-hand side. Is this a 1? It'll look at this bit location and say, is this a 1 or a 0? It's a 1, and it's true right now. So update the output on the other end to a 1 and make that true, which turns on the output to the fan. This one is the opposite because it's normally closed. So if it was a 0 in that location, this would resolve as true, and then it would make the heater true or on. So we can go back here, and so now it's cooled back down, and the temperature switch has reset. After it resets, the heater comes back on. That's that green one, that's that output there. The fan turns off, and the warning light turns off. So you're controlling all this stuff just with this one bit, all based off of one temperature switch. And this is just a real simple example. There's a million different ways you can use these internal bits. And they're calling it a flag. Use it as a flag. So this flag would be, call it overtemp flag. So every time that overtemp flag goes true, warning light comes on, fan comes on, heater turns off. So just to reiterate one more time, it's just a transistor in the memory that can be on or off. And you can use it like a relay coil, turn it on or off, and assign a bunch of other contacts to change based on the state of that memory location, whether it's a 0 or a 1. And it's not physically changing anything on the exterior of the PLC. It's all internal to the PLC. And you have tons of them to use, so you should definitely use these instead of actual outputs if you don't actually want to turn anything in the real world on or off, and you're just using it as like a relay for other internal bits. You should definitely use these. That's what they're there for. They also mentioned integers, which seemed like a weird thing to do. They said you could use an integer bit as a flag. This is not a 0 or a 1. This is any real number, any whole number, any positive real whole number can go in here. And you don't use these generally if you're only using a bit, a 0 or a 1. There's no reason to use these. If you go to, so N7:0, it's in decimal right now. If you go to binary, you'll see that location is actually 16 bits. In binary, or in the binary table, you can just use one of those individual bits, but when you go to the integer table, the idea for the integer table is that you would use it as decimal, and you can put a whole number in here. So you can put like 25. Like if you're doing math functions in here and you're getting a number from somewhere else, or you're getting a number from a counter or a timer, you can put that in this memory location. So this could be like 362 or something could go in here. But it can't go in the B3 locations. The B3 bits can only be on or off. So it doesn't make sense in this example to use an integer location as a flag for anything. I'm not really sure why they did that. And they also called it integer bit, and it's not an integer bit. The integer is actually 16 bits, and it's used to hold a whole number, not a binary digit, a decimal number, I should say. Hopefully that clears some things up and makes more sense. But yeah, that's how this would be an overtemp flag for all of these. And the way it's going to be used in the example for the project the project 4 for the door sensor is that you're going to use this to kill the up and down motors, both of them. If there's a situation where the motor up is energized and you press the close button, if both of those are true, it's going to drop out the enable bit. So I have an enable bit over here. You'd have normally closed contacts, and when this goes true, those will open up, and those will kill the power to both motors. When you have it try to go the opposite direction, so it doesn't reverse immediately, it stops everything. There's a little bit more to it than that, but I'm going to have an example of that here too in a future video. Okay, hopefully that's helpful.